Here we're going to be looking at question 24 of the ENGAA 2018 paper. In this question we have two different steps. First, we're told that we have a fission reaction where a neutron collides and is absorbed by a uranium-235 nuclide. The resulting nuclide then decays into a series of things: a bromine-88 nuclide, a lanthanum-145 nuclide, and some neutrons. It's worth noting at this point that we're told that the bromine nuclide has 35 protons in it, yet we're not told how many protons are in the lanthanum nuclide. Then, in the second part of the question, we're asked to consider the lanthanum nuclide again. Here, it emits a beta minus particle and becomes an unknown nuclide. The question then asks us A, how many neutrons are emitted by our fission reaction, and B, the number of protons in our final nuclide in the second step of the question. So first, let's try and find the number of neutrons emitted by the fission reaction. Now, we know the number of neutrons should be conserved in this reaction, so we can compare the initial number of neutrons to the final number of neutrons. Initially, we have the one neutron which collides with the number of neutrons in the uranium nuclide. Now, since the top number, 235, is the atomic mass of the nuclide and 92 is the proton number, taking 92 from 235 should give us the number of neutrons in the nuclide. This gives us a final initial number of neutrons, of 144. Next, we can look at the final number of neutrons. So, we find the number of neutrons in the bromine nuclide, which is its atomic mass, 88, take away the proton number of 35, plus the number of neutrons in the lanthanum nuclide, which is its atomic mass, 145, take away the unknown number of protons in that nuclide. Then we also have the number of neutrons n, which we're trying to find. Now we can see straight away that the number of neutrons in the bromine nuclide is going to be 53. However, we don't know how many neutrons are going to be in the lanthanum nuclide, since we don't know how many protons there are in that nuclide. To find this number of protons, we can go ahead and look back at our reaction. So, just as the number of neutrons is conserved, the number of protons should be conserved. Initially, we have 92 protons, and then afterwards we know we have 35 protons in the bromine nuclide, but the rest should be in our lanthanum nuclide. Therefore, we can see that the number of protons in the lanthanum nuclide is going to be 92 minus 35, which will be 57. Substituting this value of 57 in, we find that the number of neutrons in our lanthanum nuclide is going to be 88. Since the number of neutrons is conserved, we can equate our initial number of neutrons, 144, to the expression we have for the final number of neutrons. Doing this, we can solve for n, which should give us 3. For the second part of the question, we need to consider the beta decay of lanthanum. Now, to do this, we need to remember what beta decay is, and it is essentially a neutron decaying into a proton and a beta minus particle. If you ever have trouble remembering which particle decays into which, we can go ahead and look at conservation of charge. We know that initially the neutron has a charge of 0, and afterwards the proton has a charge of +1 and the beta minus particle has a charge of -1. So the initial and final charges are both 0, which matches up to conservation of charge. Therefore, the process of beta decay shall increase the number of protons in our nucleus by 1. So, since we start with 57 protons in our lanthanum nuclide, the beta decay shall add 1 to this, giving 58 protons in our final nuclide. This matches up with answer H.